whereas A dot B is the same as B dot A. We will encounter cross products when we deal with torques and when we deal with angular momentum, which is not the easiest part of 801. Let's take an extremely simple example. Again, I don't mean to insult you with such a simple example, but you will get chances, more advanced chances on your assignment. Suppose I gave the vector A is x roof. It's a unit vector in the x direction. That means A of x is 1. And A of y is 0, and A of z is 0. And suppose B is y roof. That means B of y is 1. And B of x is 0, and B of z is 0. What now is the dot product, the cross product A cross B? Well, you can apply that recipe, but it's much easier to go to the x, y, z axis that we have here. A was in the x direction, the unit vector, and B in the y direction. I take A in my hand, I rotate over the smallest angle, which is 90 degrees to y, and my corkscrew will go up. So I know the whole thing already. I know that this cross product must be z roof. The magnitude must be 1, that's immediately clear, but I immediately have the direction by using the corkscrew rule. Now, if you are very smart, you may say, aha, you find plus z only because you have used this coordinate system. If this axis had been x and this one had been y, then the cross product on x and y would be in the minus z direction. Yeah, you're right. But if you ever do that, I will kill you. You will always have to work with what we call a right-handed coordinate system. And a right-handed coordinate system, by definition, is one whereby the cross product of x with y is z, and not y minus z. So whenever you get in the future involved with cross products and torques and angular momentum, always make yourself an xyz diagram for which x cross y is z. Never, ever make it such that x cross y is minus z. You're going to hang yourself. Because for one thing, that wouldn't work anymore. So be very, very careful. You must work, if you use the right-hand corkscrew rule, make sure you work with the right-handed coordinate system. All right. Now the worst part is over. And now I would like to write down for you. We pick up some of the fruits now, although it will penetrate slowly. I want to write down for you equations for a moving particle, a moving object in three-dimensional space. A very complicated motion, which I can hardly imagine what it's like. It is a point that's going to move around in space. And it is this point, P. This point P is going to move around in space. And I call this vector OP. I call that now vector R. And I give it a sub-index T, which indicates it's changing with time. I call this location A of Y. I'm going to call that Y of T. It's changing with time. I call this X of T. It's going to change with time. And I call this point Z of T, which is going to change with time, because point P is going to move. And so I'm going to write down the vector R in its most general form that I can do that. R, which changes with time, is now X of T, which is the same as A of X there before, times X roof, plus Y of T, Y roof, plus Z of T, Z roof. I have decomposed my vector R into three independent vectors. Each one of those change with time. What is the velocity of this particle? Well, the velocity is the first derivative of the position. So that is dr dt. So there we go. First the derivative of this one, which is dx dt x roof. I'm going to write for dx dt x dot, because I'm lazy, and I'm going to write for d2x dt squared x double dot. It's often done, but not in your book. But it's a notation that I will often use, because otherwise the equations look so clumsy. Plus y dot times y roof plus z dot times z roof. So z dot is dz dt. What is the acceleration as a function of time? Well, the acceleration as a function of time equals dv dt. So that's the second derivative of x versus time. And so that becomes x double dot times x roof plus y double dot times y roof plus z double dot times z roof. And look what we have now accomplished. It looks like minor, but it's going to be big later on. We have a point P going in three-dimensional space. And here we have the entire behavior of the object as it moves its projection along the x-axis. This is the position, this is its velocity, and this is its acceleration. And here you see the entire behavior on the z-axis. This is the position on the z-axis, this is the velocity component in the z direction, and this is the acceleration in the z-axis. And here you have the y. In other words, we have now a three-dimensional motion we have cut into three one-dimensional motions. This is a one-dimensional motion. This is a behavior only along the x-axis, and this is a behavior only along the y-axis, and this is a behavior only along the z-axis, and the three together make up the actual motion of that particle. So what have we gained now? This looks like a mathematical zoo. You would say, well, if this is what it's going to be like, it's going to be hell. Well, not quite. In fact, it's going to help you a great deal. First of all, if I throw up a tennis ball in class like this, then the whole trajectory is in one plane, in the vertical plane. So even though it is in three dimensions, we can always represent it by two axes, by two-dimensionally, a y-axis and an x-axis. So already the three-dimensional problem often becomes a two-dimensional problem. We will with great success analyze these trajectories by decomposing this very complicated motion. Imagine what an incredibly complicated arc that is. And yet we are going to decompose it into a motion in the x direction, which lives a life of its own, independent of the motion in the y direction, which lives a life of its own. And of course you always have to combine the two to know what the particle is doing. We know the equations so well from our last lecture from one-dimensional motion with a constant acceleration. The first line tells you what the x position is as a function of time. The index t tells you that it's changing with time. It is the position at t equals 0 plus the velocity at t equals 0 times t plus 1/2 ax t squared if there is an acceleration in the x direction. The velocity immediately comes from taking the derivative of this function, and the acceleration comes from taking the derivative of this function. Now, if we have a motion which is more complicated, which reaches out to 2 or 3 dimensions, we can decompose the motion in 3 perpendicular axes, and you can replace every x here by a y, which gives you the entire behavior in the y direction, and if you want to know the behavior in the z direction, you replace every x here by z, and then you have decomposed the motion in 3 directions. Each of them are linear. And that's what I want to do now. I'm going to throw up an object, a golf ball or an apple, in 26/100. And we know that it's in the vertical plane, so we only deal with a two-dimensional problem. This being, I call this my x-axis, and I'm going to call this my y-axis. I call this increasing value of x, and I call this increasing value of y. I could have called this increasing value of y. Today I've decided to call this increasing value of y. I'm free in that choice. I throw up an object at a certain angle, and I see a motion like this. Boing, and it comes back to the ground. My initial speed when I threw it was v0, and the angle here is alpha. The x component of that initial velocity is v0 cosine alpha, and the y component equals v0 sine alpha. So that's the begin velocity in the x direction, and this is the begin velocity in the y direction. A little later in time, that object is here at point P, and this is now the position vector, which we have called r of t. That's this vector. That's the vector that is moving through space. At this moment in time, x of t is here. And at this moment in time, y of t is here. And now you're going to see, for the first time, a big gain by the way that we have divided the two axes, which live an independent life. First, x. I want to know everything about x that there has to be known. I want to know where it is at any moment in time, velocity and the acceleration, only in x. First, I want to know that at t equals 0. Well, at t equals 0, I look there. x0, I can choose that to be 0. So I can say x0 is 0, that's my free choice. Now I need v0x. What is the velocity? The velocity at t equals 0, which we have called v0x, is this velocity, v0 cosine alpha, and is not going to change. Why is it not going to change? Because there is no a of x. So this term here is 0. We only have this one. So at all moments in time, the velocity in the x direction is v0 cosine alpha. And the a of x equals 0. Now I want to do the same in the x direction for time t. Well, at time t, I look there at the first equation. There it is. x0 is 0. I know v0x, that is v0 cosine alpha. So x of t is v0 cosine alpha times t. But there is no acceleration, so that's it. What is vx of t? The velocity in the x direction at any moment in time. That is that equation. That is simply v0x. It is not changing in time because there is no acceleration. So the initial velocity at t0 is the same as t seconds later. And the acceleration is 0. Now we're going to do this for the y direction. And now you begin to see the gain for the decomposition. In the y direction, we change the x by a y. And so we do it first at t equals 0. So look there. This becomes y0, I call that 0. I can always call my origin 0. I get v0y times t. Well, v0y is this quantity, it's v0 sine alpha, v0 sine alpha. This is v0 sine alpha That is the velocity at time 0, and this is 0. At time 0. This is 0 at time 0. What is the acceleration in the y direction at time 0? What is the acceleration? That has to do with gravity. There is no acceleration in the x direction. But you better believe it, there is one in the y direction. So only when we deal with the y equations does this acceleration come in. Not at all when we deal with the x direction. Well, if we call the acceleration due to gravity g equals plus 9.80, and I always call it g, what would be the acceleration in the y direction, given the fact that I call this increasing value of y? Minus 9.8, which I will also say, always call minus g, because my g is always positive. So it is minus g. So that tells the story at t equals 0 in the y direction. And now we have to complete it at time t equals t. At time t equals t, we have the first line there. y0 is 0. So we have y as a function of time. y0 is 0. So we don't have to work with that. Where is my... So this is 0. So I get v0y times t. So I get v0 sine alpha times t plus 1/2, but it is minus 1/2 gt squared. And now I get the velocity in the y direction at time t. That is my second line. That is going to be v0 sine alpha minus gt, and the acceleration in the y direction at any moment in time equals minus g. And now I have done all I can to completely decompose this complicated motion into two